G'day everyone. My name's Philip Heath. I'm with the Geological Survey of South Australia. I'm a geophysicist there. I'm the lucky guy who gets to look at all the company geophysical data as it comes in as part of annual reports. And today I'm going to do something a little bit different. I'm going to talk about the geophysical landscape of the Western Gawler. It's not going to be a particularly technical talk. It's going to be a little bit lighter. And yeah, let's get started. So I'm going to talk about just 3 geophysical techniques. There are a lot of geophysical techniques out there, but I'm just going to focus on 3. The first one being magnetics. Of course, I'm sure everyone's familiar with magnetics here. We're looking at measurements of the magnetic field of the Earth, either magnitude and direction or just magnitude. And from that we can infer what's happening, a little bit about what's happening underground. We're very fortunate in South Australia to have the GCAS survey, which was completed really just prior to GP2, and we'll look at some of that data today. I've stolen this slide and the next one from a colleague, Anthony Reid, and I love showing these 2 slides because they really demonstrate the value of the geophysical data, and in this case especially the magnetics. This is a geological map of an area out in the Western Gawler, just north of Fowler's Bay, and you can see there are a handful of geological units there. These are the near surface units. These are the regolith units, the tertiary sediments. All of this is masking what's happening underneath, right? We don't have any information on the bedrock. When we switch on the magnetics, though, we get this wonderful image where we can see a lot of information. And I'll just bring up the laser pointer so I can point at things on the screen. Yep, red on red. Good for us colourblind people. I can't change colour. That's all good. So when I talk about the landscape, I want to sort of talk about I like to think of it in terms of wavelengths, right? So that there are large features, the long wavelength data, and there are the smaller features, the short wavelength data. So in here we can clearly see large red areas. These are sort of what I would call the large long wavelength features, and then there's the blue areas. Okay, again, the sort of broad brush strokes. But when we look at the detail, there's really quite a lot in there. We can see folded geology. We can see the shear zones. Claire was talking about shear zones earlier. There are plenty out there, and even within the high wavelength, the long wavelength areas, we can see a lot of detail in short wavelength. So we can see geological units folding around here, and we can see them cross-cutting each other too. So there's a huge amount of information we can get out of the magnetics. So heading a little bit further north, the colourful image here is the magnetics of the area, all GCAS data. Just for reference, the Trans-Australia Railway line is cutting through the middle here. Challenger gold mine up here, Jacinth Ambrosia to the south. The boundary here is actually the boundary of the gravity survey, which I put on there just for reference. And we can have a talk about the texture of this area. I think Claire described this area up here as the bland zone, and she had a red area over here as well. So there's a lot happening here. I guess some of the features that jump out to me, of course, is this long linear feature here, the Karari shear zone. I think it's the Talakutra shear zone further to the south, and then the Kurabi coming up around here. The other features that jump out are the dolerite dikes, the Gairdner dike swarm, long thin features. These are igneous intrusions, and they extend quite significantly through South Australia. The real bonus of the GCAS data is really in the detail. If I jump back in time to our previous state image, we can still see a lot of those features. We can still see the shear zones. We can still see the dolerite dikes. So to really appreciate and hopefully maybe even show you some features you might not have seen yet, we can look at some detail. So again, this is in the north of that area I was showing previously. We can see the dolerite dikes here, we can see the shear zones, but we can see some really subtle features cross-cutting the dikes, right? These north-south features. Going back in time, oops, wrong way. Going back in time, we really couldn't see them. We also had issues with survey busts between different surveys. And if we go back even further in time, we can see we were getting issues with like beading, just trying to image these dolerite dikes using the software we had at the time. You know, they'd show up as these almost like necklaces rather than single coherent lines of data. Yeah, and I think some colleagues of mine were pointing out that the dikes, you know, extend further up here, you know, right into the north of the area. It was very hard to pick them out before. So yes, this is that bland zone, but there's a lot of detail in there, and we can see, you know, some texture here, which I think this sort of texture relates more to igneous activity. Okay, let's just skip ahead and talk more about gravity. As part of GP2, we did acquire new gravity. Anyone not familiar with it, when I'm talking about gravity, I'm talking about acceleration due to gravity. I'm not talking about black holes colliding in space and emitting gravity waves. This is something much more local. We have these instruments, these little grey boxes. They measure the acceleration due to gravity. So if you drop something, it accelerates. We can measure that. If it's a slightly higher acceleration, it means there's more dense material underneath the gravity meter. So dense rocks, gold, iron, that sort of thing. If it's a low acceleration, we're looking at the softer rocks, so the sandstones, the more porous rocks. So the GP2 gravity data has been merged in with the whole state, and it looks a little bit like this out here. You will notice some differences between this and the magnetic image, because there are some areas where there seems to be quite a lot of detailed resolution, but there are areas where we just don't have that, right? So up here in the Maralinga area, further south down here, we just don't have that much information. I think the stations out here, the gravity stations, the measurements are spaced of the order 7 k's apart. So we just don't have the sort of information that we do in areas like this where we conducted the GP2 survey. Again, we can see those broad features, the Karari shear zone up here, and we can even pick out some of the other shear zones that Claire talked about earlier. Just for contrast, our previous Bourget image for the state looked a little bit like this, pre-GP2. We can see some of the features. You know, we can see this crack here, which we'll talk about later, the Mulgathing trough, through this large red unit here, and we see, you know, quite a few of these large red units around the place. So just focusing in on the current data, and just putting in the gravity survey boundary now, you can see, you know, that corresponds to the increased resolution there. I think we're going to zoom in now. No, we're not. We're going to talk about derived products and first vertical derivative. This is the first vertical derivative image. I love showing these in black and white because the eyes are really drawn towards the long linear features, and it's here we start to see the detail in this feature here, the Mulgathing trough, as well as the paleo channels just to the north, the Challenger paleo channels, and of course the Willera trough and the younger Garford paleo channel to the north, and all these paleo channels out here too. So there's a lot of texture. This one VD also shows some linear features to the south, and my eye is drawn towards this little feature down here, sort of shaped like a boomerang. I'm not sure if that's a paleo channel as such, but perhaps a bit more work is warranted down there. There's also some more subtle features which perhaps with more detailed surveys we might be able to resolve better. This is possibly another paleo channel down here. Zooming in, that feature that's possibly possibly a paleochannel is down here. The whole survey was covered 2K by 2K gravity stations with a detailed 1K by 1K area here. We can see that there are some detailed surveys in the area which have merged in really well indeed. This is just looking at the detail of the area, and again looking at these paleochannels and the Mulgathing Trough. I know Bao Hong later today is going to be talking about these a lot more, and we can see here sort of the width of this channel is, you know, several kilometres wide. It's like our own Grand Canyon in South Australia, albeit it's kind of buried, but that's Permian age, so that's a glacial channel, whereas these paleochannels here are a bit younger. Okay. Oh yes, I do want to point out there is another gravity survey to the south of the survey area, which only recently became public domain. It hasn't yet been merged in with the state data, but the data is available. So I've just superimposed that survey, the 1VD of that survey on top, and it does show some features too. So again, there's some features which are possibly relating to underground channels, and there's a detailed area here. So yeah, we'll be doing some work just revisiting that information. This is again just going in even more detail, really bringing up the high frequency information from some of the detailed surveys, and you can see some of the linear features to the north here. I think later on today Mark's going to talk about this light blue unit as a distinct geological block, and yeah, we have the shear zones coming up through there. So that's just yeah, a bit of a general overview of the gravity and talking about the sort of landscape there. I'd love to see some more work down to the south here. I think it's around the Windbring railway siding, because yeah, I think there's something happening there. And that's just the first vertical derivative, the same thing. And I think that's all I'm going to say about the gravity. I'm going to talk very quickly about the airborne EM before handing over to Yusin, who's going to talk even more about the airborne EM. In airborne EM, we're looking at the electrical conductivity of the subsurface. We are measuring electromagnetic fields and then calculating what's going on underground. And we're interested in areas of high conductivity, water, metals, clays, and sulfides. There's a lot of company data out there. This is just a slide showing a range of selected depth slices for the different company surveys out there, and we can see you know, these paleochannel features. That they're all different systems, so some have different colour scales and different sort of textures. Okay, so we can see the Mulgathing Trough coming up through here. But there's a lot of gaps between the surveys. So the government surveys, of course, come in, and in colour here I've shown 3 of them. This one here is the 2017 Fowler survey. We've got the Amiak area, 5K spacing airborne as part of the AusAEM program run by GA. And to the south is the far west coast area. This is quite low resolution relative to everything else. It's 20K line spacing east-west. But just to put the story together, is these government surveys help join the dots with the company survey. So we can see, for example, the Mulgathing Trough heading up this way. We can see the extension of the Garford paleochannels up the top here. So yeah, that's just a very quick overview of the geophysical landscape. There's a lot more data out there. You know, there's seismic, there's ground mag. Yeah, please do, if you want any more information about those, please do reach out. All of these images are available online, and I can easily get you some links to anything that you might be interested in. And that's all I have to say, so thank you.